All right, we just turned on the pulse tube. So here you see the doer. We got the pump cart on. Our vacuum looks good, 10 to minus 6, looks great. And we just turned on the pulse tube. You can hear the whop whop noise. That's the pulse tube. You can pulse tube's up here. Probably hear it better from in here. Now let's check the temperatures. Okay, we're at already down to 263K on the 50 Kelvin stage. That's great. So it's actually cooling down. So our pressures here look good. We got our full manual gas handling system here. So now we wait. All right, we're cooling.
I think it was 2-bar on the downstream side of the slip pump.
So it may be able to handle that. So yeah, it might be.
Like down here, right? But I'm not sure.
Yeah, let's put. What are our temperatures at?
45.
It's not bad.
Yeah, everything's come down to like 28, 30 degrees from this morning.
Yeah, and these are coming down. So the 3K stage should get to 3 to 4 Kelvin. The 50K stage will probably bottom out around 50 to 70 Kelvin. And then it's important that the mixing chambers still all come down to about 3, 4 Kelvin. That's sort of the range. And then what happens then is we pump the mix into it, and it has to condense to liquid form so we can pump on it. And it only does that at 2 bar. So it's possible that usually there's a pump on the front side to force the mix in. So we need to look for that. Yeah, so we have to figure out how we're going to pressurize this to 2 bar. The problem is that this is the dangerous part, because when you're below 1 atmosphere, 1 bar, if you have a leak, it leaks in and you don't lose helium-3. As soon as you go above 1 bar for condensation, any leaks and you lose your precious helium-3. And so we got to figure out how they pressurize the still, which is right here. We need to get this up to 2 atmospheres or so, and you have to do it really slowly. This is the annoying part. You usually have to let a little gas in to 2 bars, and then it'll condense.
Yeah.
Then you slowly open the valve. In our modern systems, a computer does this for us.
It's all coming out of the keg.
Yeah.
So there is a path that goes around that way.
So we're probably going to have to.
Down there around.
Yeah, probably through 9, and maybe that's this local pump. That may be.
And they're both scrolls. So
that local pump they may have modified it to be able to handle a 2 bar output pressure. We're gonna have to figure that out. All right, yesterday we figured out that we were missing something, and that was these things right here. This fridge uses mechanical heat switches to let us get the mixing chamber and the still stages cold. Because you want them to be very well thermally isolated when you're running the system, but while you're cooling down, you need to have them thermally connected. So these mechanical switches are doing that. So yesterday we got those working and closed them, and the mixing chamber and still temperatures started to fall. So we are currently cooling down, and everything looks pretty good. Kind of shockingly, so far so good on this. Well, we've taken a break. We're back after Thanksgiving. Before Thanksgiving, we got the fridge down to 3 Kelvin, which means everything's working. It actually is working real well. So if you come over here, you can see we're down to about 2.8 Kelvin. That looks good. All the pressures look good in the manual gas handling system. So now comes the moment of truth. We're going to start up the pumps, and we're going to try to start circulating the helium-3, helium-4 mix through the through the dilution unit. First, we got to get some liquid nitrogen. So that might be the next order of business. All right, Hugh filled up the liquid nitrogen doer. Now we're going to go install it.
Oh, safety precautions and didn't ride with it?
Very safe. Good job. Nice work. Sucked into the nitrogen trap, because again, using the plug, you know, like that. You gotta, if the plugs, you gotta warm all the way back up to room temperature basically and start over. Okay.
It's keg one.
Which one is keg one?
It's one on the left. There's like two on the left.
This guy here?
Yeah.
So I'm gonna open it.
Okay.
Okay. So
Yep. Yeah. I brought it back up. Okay. So return.
you can see the temperatures have already gone up from about 2.8 Kelvin to 3.07 Kelvin up here. Now we've got mix in the lines. The expensive helium-3 is there. You'll notice we did find an instruction manual. It's for a slightly older fridge that used liquid helium to cool instead of a pulse tube, but the dilution fridge part seems similar. So hopefully these instructions will work.
Mix temperatures went up a bit, maybe.
Yeah, so stills at 2.6, mixing chamber is at 3.1, 3.3.
Okay. And the keg and the return pressures are still high.
Yep. And the still pressure is starting to come up too.
So, alright, so this, they do have us turn the turbo, we're not going to do that, but at this point we said wait for the mixture to cool, and passively condense, and
Okay.
This has been pretty stable for the last 20 minutes.
Yeah, but this is, so that we've gone to about half the pressure we were at to start with,
Yep.
and this has gone up significantly,
Yep.
whatever that means.
Yeah, so it's colder.
It's colder. Thermometry, yay. All right, so now we're going to crank.
So it's going to crank, yeah.
Okay.
So that's close, 11, open 8, and then I'm going to open 7, and we should expect to see return go up, right?
Yeah,
I want to keep the
and you're going to keep it below in the range. Okay. Coming up. It still went high. We would call this in my fridge high pressure condensing. And so this should now drop pretty quickly. And what should happen is that pressure in the keg, every time you do this, the pressure in the keg should drop. So when we're going to get down to what, 350 or so? Is that what it says?
let's get to 30 torque.
All the way down to 30?
I mean, in the keg?
No, I mean,
No.
In the return, when do you open again?
No, it doesn't say. This is try to keep it between 300 and 350 above.
Okay,
So I
so
can open it again now, I guess.
yeah, you could. All right, so we should keep doing this.
Just, I guess try to keep it balanced, I suppose, right?
Mine tends to shoot and mix in, so it'll condense it down to like 400, then it'll open up, go up to 700, come back down, and kind of cycle. I don't know. I think it doesn't like. Maybe they just don't want to open the valve that often, but it lets it.
Yours is an automatic.
It automatically opens and closes it.
Okay.
All right, and we're slowly sucking the mix out of the keg and condensing it into the fridge, keeping this pressure roughly constant. Got still at about 8 torr. This is a thermometer. It says reading and resistance. We don't know exactly the right curve for this, but we think it's about 800 millikelvin, which is about the right temperature. This diode box here reads out these silicon diodes or resistive thermometers, but it puts in too much power, so we disconnected these so it wouldn't heat the low temperature stages as we're getting cold. Oh, and this is, I hear the turbo spinning up. You can see this is going to drop as the turbo spins up. 930. So we are getting a little colder with the turbo on. Okay, I think this is fine. One thing we forgot to do was open these heat switches. I'm going to open both of these heat switches. Okay, those heat switches were forcing all the stages to be at the same temperature. Now they should not be doing that. And so that we wouldn't have been able to get cold if we'd forgotten those. You can hear them going. Okay, it stopped. For better or worse, it stopped. So I think we're open. All right, opening the heat switches made a difference. We're much colder now and going up faster. And I wonder if this is dropping faster.
I don't know, I can't tell.
Hard to tell. Okay. This temperature is
Actually, I think it's dropping faster.
I think it is dropping faster. Though when you open the heat switch, you do dump a bunch of heat into the stage just from the mechanical action. But it shouldn't. If the fridge is big, it's not going to be enough to matter.
That made a big difference, I think.
Okay. Yeah, that was probably keeping us from doing what we needed to do. Yeah, this is definitely going faster now. Now this looks better. All right. We're gonna have to update those instructions because the other switches. Yeah, well, the other fridge has a 1K pot and does not have heat switches like this. They probably use an exchange gas to cool the stages and might have had a charcoal getter to absorb the exchange gas. But this one has those heat switches. So good catch by me, and we're continuing to go down. So we have to have enough mix in the system to fill up the mixing chamber. So we're condensing this helium-3 mix in here, and then when there's enough of it, it fills up the still, and then you get this phase separation between the concentrated phase and the dilute phase, and so you have to have, in order for this to work, you have to condense enough mix so that you fill up the still above the bottom here. You need that surface area in the still. So sometimes you can lose helium-4 from your circulation, and then not have enough gas to fill up the still, and your interface will be in this tube, and then you don't have enough surface area for the dilution effect to really work. So that's why you need the right ratio of helium. You need enough helium-3 to get you the cooling, and enough helium-4 to fill the mixing chamber in the still. So we're going to condense all the gas in the keg. It'll hopefully fill all this up, and then we'll be able to do the dilution cycle and make it all work. All right, we've let the fridge circulate its mix overnight. If everything went well, it's cold. If everything went poorly, something blew up. So we will see. I guess we won't see because the door is locked. We need to get the... This is the wrong lab. That might explain it. This is the right lab. And the door here is locked too. Hugh's got the key, so I'll come back later and check. How's it look?
Mostly good.
All right, so the still is at 0, which is okay. The keg has 67, so we let some gas back in the keg through the release valve, huh? Okay. 638, it's a relatively high circulation pressure. I would agree. My fridges are usually lower than that, but what do we have over
So
here?
77 kilo ohms.
That's high, right?
Yeah, that's pretty high.
So if we look at your chart here, 77 kilo ohms is like 50, below 50, is 50 millicolumn. That is successful. High five. We got this fridge working. This is a functional dilution refrigerator. I am pretty shocked that we got this working. I mean, the main things that were broken were the pump card had a bad solenoid valve. The turbo controller here was broken, so Hugh got this guy out of and replaced it. with one that we had lying around. Was that it?
The pressure manometer.
Oh yeah, this pressure sensor gauge needed to be replaced. The thing that really shocks me is that the compressor water cooling works. So if you hear that wop wop noise, that is coming from a big helium compressor. It's like a 15 kilowatt compressor that is constantly taking helium and compressing it up to about 300 psi, and then it circulates through this loop and that's how this mechanical cooler works. But it has a water cooling system which circulates water to cool it. That's been sitting untouched for 6 years and it's still working, and that is vaguely shocking given what I know about the water circulation systems in Broida here. So this fridge is functional, and now the next thing we're going to do is warm it up, and then we got to move this entire system to a new lab, and that is going to be a challenge. Thanks for coming with us on this journey of building this dilution refrigerator and making sure it works. Stay tuned. We will have an episode, I think, where we move this to the new lab, and that is going to be a real challenge.